There are a few principles of reaction kinetics that we need to understand for introductory organic chemistry. In the next few minutes, I hope to convince you that what we need to know is straightforward and manageable and easy to apply in our circumstances. By the term reaction kinetics, we mean the rate of the reaction. How fast or how slow is this reaction? And the reaction rate can be described by an equation that has two components. You'll notice immediately that as the concentration of the reactants increases, the rate increases. This makes sense. The second component is the rate constant. And there are two components of the rate constant that I want to call your attention to. One is temperature. As we increase the temperature, reaction rates increase. This is buried in that rate constant, which obviously then is for a specific temperature. The second component of the rate constant that I want to focus attention on, and this is our main focus of attention, is the activation energy. And for the kinetics of organic reactions, this activation energy is really crucial. Take a look at a couple of examples. Here's a reaction where an alkyl bromide splits into two. And we can rationalize what's happening here by using our arrow pushing to follow the electrons. A pair of electrons that are involved in that carbon-bromine bond go with bromine to form bromide and break the bond. This leaves a positive charge on the alkyl group. And here's the lone pair, the unpaired pair of electrons that were involved in the bond. The rate equation for this reaction follows the form we just saw. There's a rate constant, and then secondly, the concentration of the alkyl bromide. I'm going to write that as RBR. R is the abbreviation for alkyl group. So this guy is abbreviated RBR. And the rate equation has the concentration of one reactant and the rate constant term. Because there's only one reactant in the rate equation, we call this a first order reaction. And for our purposes, the key component of that rate constant is the activation energy. And how do we get a handle on the activation energy? Look at the energy diagram. When we look at an energy diagram, we simply look at the difference in the energy of the reactants and the top of this hump where the transition state occurs to determine the activation energy. Here it is. And what you'll see when we compare this to another reaction, that this is a relatively large activation energy. It's a pretty big energetic hump that the reactants have to surmount. The activation energy is large, and so the reaction is relatively slow. Here's a second example. In this example, we have two reactants, chloride and the alkyl bromide. The chloride is replacing the bromide. Using our arrow pushing convention, we can follow what's happening with the electrons. Electron pair with chloride is being used to form a new bond with carbon. And this bond between carbon and bromine, that pair of electrons is going with bromide. And the rate equation follows the same format that we've looked at. In this case, that we have the concentration of two reactants, the alkyl bromide and the chloride, showing in the rate equation. So the concentration of both affects the rates. Increase the concentration of one will make more product faster. Increase the concentration of the other will make product faster. Because there are two reactants in the rate equation, we call this a second order rate equation. And again, for us, the key component of that rate constant is the activation energy. And we can get a handle on that activation energy by looking at the energy diagram. And when you take a look at that energy diagram, you see that right away that the difference in energetics between reactants and the transition state isn't very large. So this reaction will be faster because it has a lower energy barrier to surmount. So smaller activation energy, faster reaction. So folks, that's it. You get a handle on a few simple principles as I've outlined here, and you'll know all you need to know to apply kinetics for understanding organic reactions.